We're now going to use a tool that can help establish for us where the real zeros may actually lie. And this is called an upper and lower bound test. And just a description of that, if we synthetically divide a polynomial function by a number, and all of our elements of the depressed polynomial, if they're all positive, then that would in fact be an upper bound. In other words, there's no real zeros greater than that number. And if we also divide a polynomial by a number, and if our quotient is alternating positive and negative numbers, one positive, one negative, or one negative, one positive, and they're all alternating, then that establishes a lower bound. And so between the upper and lower bounds, all the real zeros will lie between that interval. So let's get a little practical experience with that. Now we got this function g of x equals 6x to the fourth plus 70x cubed minus 21x squared plus 35x minus 12. Now we know that we could have as many as 4 rational real zeros from the rational zero theorem. And let's just kind of go about and try to figure out, okay, well, what could they all be? So I'm looking at, we got P over Q, all the factors of the constant over all the factors of the lead coefficient. So let's see, we could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. I'm doing all the factors of 12, plus or minus 6, and plus or minus 12. Let's see, 1 times 12, 2 times 6, 3 times 4. Okay, that would be all of those over all the factors of the lead coefficient, which is 6, which is again plus or minus 1, plus or minus 2, plus or minus 3, plus or minus, that's it, plus or minus 6. I'm about to leave off the last one, plus or minus 6. Now let's determine what all the possible rational real zeros may be. So let's see, we can start off with plus or minus 1, the first list, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Well, if I divide all those by plus or minus 1, I'm going to get the same thing. But when I divide by plus or minus 2, I can then add to that list plus or minus 1/2, plus or minus 3/2. I'm now dividing everything by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. And 12 divided by 4 is 6. Now let's work on the 3's. Well, now I got plus or minus 1/3, plus or minus 2/3, plus or minus the 3. Okay, 4 plus or minus 4/3. And that takes care of the 3's because 6 divided by 3 is 2 and 12 divided by 3 is 4. Now we do the 6's, and I could have plus or minus 1/6. Man, I got a lot, don't I? Let's see, 2 divided by 6 is 1/3. I already got that. 3 divided by 6 is 1/2. I already got that. 4 divided by 6 is 2/3. I got that. And then 6 divided by 6 is 1. We got that. 12 divided by 6 is 2. This is all of our possible real zeros. Now, I had already graphed this, and one of the things that the graph did not fit on the screen, but one of the things I noticed from the table, I've got a 0 between 0 and 1 because I see a sign change right here. And that sign change tells me that somewhere between 0 and 1, we crossed the x-axis. Now, all my numbers from there are getting really large, but going up this way, they're getting really small. Well, let's see. On the negative side of things, well, let's deal with between 1. I want to first find out, is 1 an upper bound? So let's go to the next screen. All right, so I'm going to do, if 1 is an upper bound, I'm going to synthetically divide this. Let me change the color on this. If I synthetically divide by 1, and if all my elements of my quotient are positive, then 1 is in fact an upper bound. Then I could just have to worry about the lower bound. So let's see what we got. So I bring down the 6. 1 times 6 is 6. 70 plus 6 is 76. 1 times 76 is 76. Negative 21 plus 76 is 55. Everything's positive so far. 1 times 55 is 55. And 35 and 55 is what? 90. And 1 times 90 is 90. And 90 from negative 12 is 78. So these are all positive. So that tells me that 1 is an upper bound. And even though from that table I couldn't tell for sure, I did that test. Now, on the negative side, we could have a plus or minus 12 as one of our possible rational real zeros. So what about, let's try negative 13. And if negative 13 is a lower bound, then guess what? We're going to have alternating positive and negative numbers. So let's go. We got 6, 70, negative 21, 35, and negative 12. Let's bring down the 6. I didn't leave myself much room. All right, well, let's see. Negative 13 times 6, and I've already worked this out, so I'm not going to have to pause and use the calculator. That's negative 78. 70 minus 78 is negative 8. Okay, well, I got a positive and a negative so far. Negative 13 times negative 8 is 104. Well, negative 21 plus 104 is 83. I'm back to positive again. Negative 13 times 83 is actually negative 1079. Plus 35 is negative 1044. I'm looking pretty good. Positive, negative, positive, negative. And negative 13 times negative 104, oh, that's a nice little number, 13,572 minus 12 is 13,560. So my quotient is all alternating positive and negative numbers. So negative 13 then is a lower bound. So we got between the interval of negative 13 and 1 is where all the rational real zeros are going to lie. Now I got to find the real zeros. Well, let's try negative 12. So I got negative 12 in the box. This one I haven't worked out. So I got 6, 70, what was it, negative 21. And if it's a real zero, I got to have 35 and negative 12. If it's a real zero, I've got to have 0 for a remainder. All right, let's bring down to 6. Negative 12 times 6 is negative 72. 70 minus 72 is negative 2. Negative 12 times negative 12 is 24. Negative 21 plus 24 is 3. Negative 12 times 3 is negative 36. 35 minus 36 is negative 1. Well, Shazam. And negative 12 times negative 1 is what? 12, positive 12. And negative 12 plus 12 is 0. So 12 is one of my real zeros. And I got 3 possibly more. Well, we know that 1 was an upper bound. And we had several possibilities in there. 1/3, 1/2, 1/6, 2/3. All of those were less than 1, between 0 and 1. Well, let's try 1/3 on this depressed polynomial here. Bring down the 6. 1/3 times 6 is 2. Negative 2 plus 2 is 0. 1/3 times 0 is 0. 3 plus 0 is 3. 1/3 times 3 is positive 1. And negative 1 and 1 is 0. So 1/3 is a rational real zero. Now, what have I got left? I have this depressed polynomial then works out to be 6x, I'm 2 away from x to the 4, so 6x squared minus 3. All right, well, let's see. Plus 3, excuse me. 6x squared plus 3. Well, let's factor out a 3. That'd leave us with 2x squared plus 1. And let's set 2x squared equal to 0. And then we're going to subtract 1 from both sides. 2x squared equals negative 1. Well, right there I could pause and say, so I don't think I'm going to have any more real zeros. But let's keep going. So we divide both sides by 2, and I got x squared equals negative 1/2. And then when we take the square root of both sides, x is equal to plus or minus the square root of negative 1/2. Well, that's not a real number. That is a complex number or an imaginary number. And so therefore, in this case, where our upper and lower bound were between negative 13 and 1, and we found 2 real zeros at 12, negative 12, I need to get that as negative 12, and 1/3, and our other 2 zeros are complex numbers or imaginary numbers, well, we've done it. We have found all the real zeros, and while using the upper and lower bound test. Wow. And this was a tool, I think, if you can imagine, would have been pretty beneficial prior to the days of calculators. Maybe with the calculators, a little bit less so. I can tell you, and I encourage you to graph that on the calculator. You're going to have to play around with the window screen to actually see where those are, because negative 12 is going to go beyond what you would see in a regular default setup of x minimum of negative 10. So it's still useful, and we'll probably try another one in a bit.